So mainly doubts were among the how revolution time changes with gamma or how it remains constant with gamma. Even means energy is changing, but revolution time is decreasing. This kind of questions and what is the sector type dipole magnet and how it is focusing in the vertical plane and like and related to that means how if horizontal focusing is there, why it is in vertically defocusing and that's kind of thing. So I will show some slides which will cover those concepts which will be useful to understand the answer of these problems.
Okay.
So are you able to see
Yeah,
the
yeah, we can see.
screen?
Yeah.
Okay. So actually there were some questions asked about how revolution time is changing with gamma. Sometimes it seems that if energy is increasing, always there should be the change in the gamma or revolution time. So actually revolution time basically which we have derived is T revolution is 2 pi m upon qp into gamma. Here m is the rest mass of that particle which we are considering. Q is charge of that particle and B is the applied magnetic field, like in this cyclotron or microtron and like that. Where dipole magnets, actually B is related to dipole magnet, which is used to bend the design trajectory. So here that B should be there and it is multiplied by gamma. This is a simple relation which we can derive just using centripetal force equation gamma mv square by r is equal to qvb, where we are assuming that V is perpendicular to the B applied magnetic field. So here we can see that what is gamma? So gamma is definitely the total energy, is total energy of the particle, which is scaled by the rest energy of the particle. So if a particle is having rest energy 1 GeV, then a total energy of 2 GeV, it is having only gamma 2. While for a particle which is having 0.5 MeV, let us say rest energy like electron, in that case 2 GeV means 4000 gamma value. So gamma is very different for the same energy for different particles. Means for 1 GeV, if we are having kinetic energy of 1 GeV for the proton, the gamma is just 2. And in the case of 1 GeV electron, gamma is 2000. So this makes a hell of difference between the revolution time for the proton and for the electrons in the given magnetic field B. So now this E can be write down rest energy plus kinetic energy because this is the total energy. So total energy is the kinetic energy part plus rest energy part. So gamma will be E0 plus Ek by E0, which we can write down as 1 plus Ek by E0. So if kinetic energy is much less than rest energy, then gamma is approximately 1. Means even if uh, so say 10 MeV proton, so Ek by E0 will be 10 by 1000, like that. So it will be 1.01. So 001. So gamma is very, very closer to 1. In the case of non-relativistic regime, means when kinetic energy of any particle which we are considering has energy much lesser than its rest energy. So in that case, gamma remains constant near to 1, and this equation T revolution actually practically independent to gamma in that case. But when gamma becomes very high, means kinetic energy is much higher than the rest energy of the particle, then definitely this equation is not practically independent to gamma. Instead, if gamma increases, they say that on the same orbit length, T revolution will increase. So this change in gamma basically decides how we are synchronizing the machine for practically running it. So means when we are synchronizing a machine which is working mainly in non-relativistic regime, we are taking gamma as a constant and our T revolution becomes constant. So this is the main thing which is used in classical cyclotron. In classical cyclotron, basically gamma remains almost constant. So T revolution also remains constant. So T revolution does not change by a large number. Then definitely synchronization can be done as T revolution by taking as integral multiple of the TRF. TRF is the applied RF electric field, time period of the RF applied field, which is used for particle acceleration. So this relation is for classical cyclotron. And that's why in classical cyclotron, we cannot push the particles to much higher energies. It will be very low compared to rest energies. Means in classical cyclotron, we can go up to 50 or 60 MeV and like that. Definitely, there are some variation of the cyclotron as AVF, azimuthal varying field cyclotron, where we can raise energy up to higher values. However, in classical cyclotron, this relation holds good, and we really work up to 30, 40 m even like that. However, when gamma changes, you can calculate very easily what will be the change in delta T. Definitely delta T, these all quantities are constant. If we are not changing our applied magnetic field, then these quantities will remain constant and delta T will depend on delta gamma. And delta gamma is basically delta E. So delta T depends directly on the delta E in case if gamma is changing, like in electrons. If in electrons it becomes relativistic at very low energies also. So if it is passing through the same magnetic field again and again, so and in each turn, if it is getting energy from the RF field, the gamma changes and the revolution time also changes. And that change is actually proportional to delta E. So delta E, we are getting delta E due to applied voltage in the RF field. So if we are not changing the peak voltage of the radio frequency field and we are also keeping the fixed frequency, then this delta E remains constant. Means suppose we are in the 50th orbit and we are going into the 51st orbit, there is change in delta T. And again, if we are says we pick number 25th and 26th orbit, there will be delta T. This delta T of the 25th to 26th will be equal to 50 to 51. This is the beauty. Means this delta t in successive term remains constant. So this delta t can be used to synchronize the particle. And that is exactly done in the microtron. So in microtron, what we do, we actually make the first orbit synchronized using t revolution is equal to ATRF. A is some integer multiple. So this makes synchronization of the first orbit, and successively we can synchronize all the orbit by taking delta t is equal to BTR, because we are having same delta E in all the orbits because we are not changing the voltage. So delta E will be QV sine omega t. Here V is the peak RF voltage and omega is the RF frequency. So QV sine omega t, if we are not changing V and omega, this will be constant and delta E will be constant. And delta T is directly proportional to delta E. So delta T will also be constant number. So this equation delta T revolution is equal to BTRF, where B is some integer multiple. It will make all the orbits except first synchronized. And this equation will make the first orbit synchronized. T revolution is equal to ATRF. So in microtron, basically we have two constants, A and B. So microtron is decided by two constant, and when you will do some derivation which is given in the lectures, complete derivation is provided in the lectures, you will see if we want to obtain delta E, means change in energy in terms of these A and B parameters, you will see that in denominator there will be A minus B, and that A minus B ensures that there will be practically delta E positive always when you have A greater than B. A minus B is in denominator, so A minus B should be greater than 1 because both are integers. So minimum value possible for B is 1 and minimum value possible for A is 2. So this was asked in one of the questions, and there were some doubts that why A cannot be 1. So this is precisely the reason that if A is 1 and B is also 1, we get denominator in 0 and there will be no practically gaining in the energy, means microtron will not run. So for running the microtron, A should be greater than B. So minimum value, possible value of A is just B plus 1. And minimum value of B, because B is integer, we are taking. So for making it synchronization, the minimum value of B must be 1. So minimum value of A must be 1 plus 1 is equal to 2. So B is equal to 1 and A is equal to 2. This combination is known as classical microtron. So in microtron, using this synchronization condition, even we can energize the electrons, which becomes highly relativistic. Anyhow, you will also see that this delta E, change in energy, will be directly proportional to rest energy of the particle. Means in one turn, we have to raise energy in the order of rest energy of that particle. Means in case of electron, you have to increase the energy in one turn in the order of zero point 0.5 MeV, means 500 kV, which is possible. We can apply even 1 or 2 MV field, megavolt field in the cavities. So it is possible to energize the electron in microtron. However, in case of protons, the required change in energy will be in the order of GeVs, which is not possible. That's why microtron works only for electron, while cyclotron works only for proton. So these are complementary machine to each other. Cyclotron is basically working in the non-relativistic region for heavy particles like protons or heavy ions, and microtron is working in the relativistic region, and it works for light particle like positron or electrons. Definitely, microtron is also known as electron cyclotron sometimes. So it is a very simple and small machine basically, which can raise easily the electrons energy up to 20 or 30 MeV. It is used in some industrial applications as well as injector of the larger machines. Now there were some doubts that which type of magnet is known as sector magnet and how it focuses in the vertical direction or defocuses in the vertical direction. So we will see that. So dipole magnet means there are two poles. It is the simplest possible structure of any magnet. So this is the first pole N and this is the S. And by red color arrows, we are making the field lines from N to S. So there are pole surfaces and these are pole edges. And between these poles, there is uniform field except near the edges. Near the edges, there will be variation in the field with the distance, but deep inside, well inside in the magnet body, the field will be uniform. So suppose a particle comes from here, this is the green trajectory, and it enters into the field. So it will make some circular pressure path and it will exit from here. So this is the basic idea of dipole magnet. There are two poles and between the gap there will be uniform field, and in that gap we will launch the particle and it will have some curvature in the trajectories. So desired curvature can be obtained using the proper magnetic field or proper dipole field for a particle. So if we will see top view of this figure, the top view will be like this. A particle is coming here. This is the pole surface. And then inside this magnet, there will be a curvature in the trajectory and then it will exit from here. Now you can see when it will start circular path here, it will have certain radius of curvature. This is the radius of curvature of this path when it is inside the magnet. So just it starts circular trajectory from here to here. So there will be a radius of curvature R. And this will be the bending angle, means how much angle has been changed compared to entry at the exit of the trajectory. And if this radius vector has certain angle with this edge, magnet edge, this is designated here E1. This E1, this edge angle, this is known as edge angle. This edge angle is actually decides what type of focusing or defocusing or no action will be there in the vertical plane for a particle. How we will see that? At the exit also, there will be some edge angle E2, but for clarity, we will see only this part. The same theory will be applicable here also. So now we can say that one type of magnet we can make like this. This was in the last screen where E1 was the edge. Now if magnet shape is like this, means edge is matched with the radius of curvature. Means angle between the radius of curvature r and age becomes 0. If this is the configuration of the magnet, this dipole magnet is termed as the sector dipole magnet. In sector dipole magnet, age angles are 0. So any magnet, if we change the orientation of the magnet, that can become sector type and that can become other wedge type. Now suppose why this is known as sector. Suppose there is a uniform magnetic field. These cross are the magnetic field lines going perpendicular to this light, and this is uniform. And suppose a particle is launched here, it is making some circular path here. So here the tangent at 3 points I have drawn. These tangent shows the direction of the velocity vector at that instant. Now if make some sector of this circle, So at the entry, this velocity vector will be in the perpendicular direction of this sector, because sector is going up to the center to circumference. So this is the radius. So radius is perpendicular to the tangent. So here at the entrance, there will be a perpendicular direction between the trajectory and age. Or you can say between the radius of curvature and age, there will be zero direction, zero angle. Similar case is happening at the exit also. So if we remove magnetic field from all the space except in this sector, so now trajectory will be straight here, and when it goes inside the magnet, it will be curvature, and then there will be straight. So this kind of magnet is known sector magnet because it is derived from the sector of a circle. Now if we will see from the side, the trajectory is going like this. This is the north pole, this is the south pole, and there is the uniform magnetic field well inside the body. What happens actually at the edges? So you can see at the edges, magnetic field rise slowly and slowly, gradually. And again, at the exit edge, it falls gradually. There should be no, or there must not be any step function like that kind of thing. That is not permissible. If you will see Maxwell's equation, the step change in magnetic field is not allowed. It violates the Maxwell's equation. You can prove it very easily. You just take an imperial loop here and try to prove yourself that step function is not possible in magnetic field. So magnetic field will rise gradually here at the entry. It will become uniform here inside the body of the magnet, and then again towards the exit it will gradually falls down. So this kind of profile you will have in the space for a dipole magnet. If we will see how this gradually fall, means in this area, how field line will look like. So this is the north pole, this is the south pole, this is the mid plane, means exact plane exactly in between these two poles. So the field lines will look like this curvature type thing here. Now on the mid plane, there will be exactly vertical component, and if we go above the median plane and between the north pole, there will be a component in the vertical direction as well as in the s direction, minus s direction. Means if trajectory is in the s direction, this component will be in the minus s direction, and opposite is true for the points which are below the median plane. In that case, there will be a vertical component and a horizontal component which is in the plus S direction. So now inside the magnet body there will be only vertical component, but at the edges there will be horizontal component also. These horizontal components are actually imparting a force in the vertical direction, and that is responsible for the focusing and defocusing. Now, how this focusing and defocusing actually depends on the edge angle, we will see that pictorially. Now, suppose a trajectory which is coming towards the magnet is perpendicular to this edge. This is the orientation of a sector magnet. In sector magnet, the edge is perpendicular to the trajectory, means edge is parallel to the radius vector. Radius vector and edge both have zero angle between them. So trajectory is entering inside the magnet with the 90 degree with respect to these edges. Now at the 90 degree, if trajectory is exactly in the median plane, then definitely there will be only vertical component. Means this trajectory will be unaffected in vertical plane. This vertical component of magnetic field will impart the force horizontally. So there will be only horizontal bending of this trajectory. No vertical force will be there. Means this particle will remain in the median plane at the exit also. So on the median plane, if particle is entering inside the magnet, there will be no effect in the vertical plane. However, if particle is displaced vertically up from this median plane, what will happen? When it will comes towards the fringe field is not now exactly perpendicular. Now it has certain component in the horizontal direction also, minus bs, but that is anti-parallel to this v, because v is exactly perpendicular to the edge and bs is also perpendicular to the edge, so they will have component in the same direction as of the velocity. Therefore v cross b for this component will be 0. So again, this component will play no any role for vertical plane. Again, it will bend only horizontally. Now suppose we change the direction of entry of this particle. Means now edge angle and radius vector has certain finite non-zero angle between them. Means there is non-zero edge angle. In these two figures, edge angles were 0. So in sector magnet, we have seen that there is no vertical effect on the particle, even if we are considering the fringing field. Now if particle is coming here in the median plane, again on median plane there will be only vertical components. So particle on median plane will not feel any force in the vertical direction due to magnetic field. Due to vertical component of the magnetic field, it will feel only horizontal force. So particle on the median plane will remain in the median plane. It will not deviate from the median plane. In median plane, there will be bending horizontally. Now suppose particle is displaced vertically up from this plane. Now here again there will be a component which will be in the horizontal direction of the magnetic field, and there will be vertical component also. But now horizontal component of the magnetic field will be perpendicular to magnetic edges, while particle is coming at some angle with this. So there will be a component which will have V cross B non-zero for the horizontal component also. Means we will have now vertical force also. So if we have non-zero edge angle and particle is deviated vertically, it will feel some vertical force. And this vertical force is responsible for focusing or defocusing. Means in sector magnet, there will be no vertical effect. But if we have orientation other than sector magnet, there will be vertical focusing or defocusing depending whether the edge angle is positive or negative with respect to edge. If it is positive, then definitely there will be focusing in the vertical plane, and if it is negative, then there will be defocusing in the vertical plane. So fringing field is responsible for the vertical plane focusing or defocusing. However, in sector magnet, there will be no effect. This was the case, and this was the doubt. Actually, this is definitely a genuine doubt, because at first time study, this is difficult to grasp it. And I can recommend one very good book on it by PJ Bryant, which shows it nicely how the vertical focusing in the fringing field will take place. Now we will consider the assignment 8's problem 7, in which it was asked if there is a proton of 10 MeV. When we are saying that this is a 10 MeV proton, definitely this is the kinetic energy, because rest energy itself is 1 GeV. So when we refer to 10 MeV, means it is the kinetic energy of the proton. And if it is going into the cyclotron, and cyclotron is set to 0.5 Tesla magnetic field, what will be the revolution time? So we can see it at 10 MeV. Proton is non-relativistic and gamma is approximately 1. So T revolution will be 2 pi m upon qb, and gamma is 1, which was multiplied by here. So gamma is 1 just. So equation will be 2 pi m by qb. Just putting the value of 2 point mass 1.6 into 10 raised to minus 27 kg, here I am. Q is 1.6 into 10 raised to minus 19, and B is zero point 0.5. So you will get the answer. And the answer is 0.125 microsecond. There was some typo mistake in this problem, and option was written as 0.25 microsecond rather than 0.125 microsecond. So that is correct answer for the problem 7 of assignment 8. So from my side, I am now done.
Thank you, sir.
So
Amledu, can you go to the first slide?
yes, sir, definitely.
Uh, because I, as a student, had two doubts which I can clarify myself. I
Yes,
can
sir.
ask question and clarify also, but I
Yes,
would
sir. Yes,
like
sir.
you to clarify that.
Yes, sir.
So if you go to first slide, there you said this E naught is rest energy. Actually, it is E naught is rest mass energy.
Yes, rest mass energy, E
So,
naught.
Amit, because here some of the MSc students also may be attending, so they should not have been confused. So, E naught is uh, a rest mass energy. So, if you
Sir,
take
I actually tactically used word rest energy
no, no,
because modern literature
no,
of
people,
relativity actually discards
no,
relativistic
no,
mass variation.
yeah, see the people who are working in accelerator physics, for them it is okay.
Yes.
And they use this but the MSc students may have some problem. So
Yes, yes.
E naught is rest mass energy.
Rest mass energy. Yes.
Rest mass energy it is called. And secondly, see this confusion always come in the minds of students. We always say it is 1 GeV, while
Yes.
they study as 935 something, like
Oh, this is
931.
approximation. This is
So,
approximation.
so
Yes.
for the sake of calculations, this
Yes.
931 MeV rest mass energy of proton is taken to be 1000 MeV, so it is 1 GeV. This is only
Yes.
for the
Yes.
simplification of the calculations.
Yes. Definitely.
But
That's for
otherwise, E
electron.
naught
Yes.
is
Yes.
E naught is 0.931 MeV, GeV.
Yes. GeV.
So this is
And
only
for
just
electrons also it is 0.511 MeV, but we
correct.
generally take 0.5 MeV.
Correct. So these are only for calculations,
Yes. Yes. Yes.
simplicity of the calculations.
Okay, sir.
So, okay, thank you. Very nicely.
Thank you,
I
sir.
also learned from that.
Thank you, sir. Thank you, sir. And you also pointed out correctly that I should not use those rest energy. I actually was tactically using that word because nowadays relativity literature says that relativistic mass is not correct word. Otherwise, Minkowski space will be in trouble if we take the mass changes with velocity rather than they say gamma changes as mass remains constant.
So,
That is only the thing how we are conveying the message. But
correct.
there are so definitely we should use for MSc student rest mass energy word. That will be
This
more
one
clear to
actually,
me.
even the I think one or two people maybe from BTech also.
Yes, definitely.
So then we have to. It was nice to clarify that.
Yes. If someone has any doubt, only one person has joined. If Dhanush, you have any doubt or your query, you can ask here. All the discussion which were carried here in the live session, I have also posted on the forum with detailed answer all of these in the PDF file.
Sir, hello.
Yes.
Sir, can you please solve the third question of the eighth assignment? Am I audible? Hello.
Yeah, we can hear you. I think. Oh,
Are you able to hear?
yeah. You are
Hi.
muted actually, sir.
Yes. So in third problem is that an electron which was initially at rest has been accelerated through a potential difference of 150 keV. What will be the speed of this electron after acceleration? So 150 keV potential difference is there, and initially at rest means initial speed is zero, u is equal to zero, and applied electric field is 150 keV. What do you expect that how much force is there? Dhanush, if
Sorry,
electric
sorry,
field is
what will
applied
not?
E
Okay,
and
sir.
electron is there,
QE.
what will be the force on that?
QE.
QE, exactly. And what will be the acceleration?
Off into mv square.
Acceleration QE by m. Here 150 kV is, we can say it is in the non-relativistic region. However, you can calculate with relativistic formulation also. Okay. So if you know acceleration and it is a constant, because QE is constant, E is constant now.
Oh, okay, sir.
Okay, so you can calculate very easily.
Oh, okay, sir.
Because it is the acceleration in the direction of velocity. So really, if you will use the relativistic formulation, gamma cube will come instead of gamma. Keep it in mind. You can go through the very nicely written book on relativity, which is a very elementary book by Resnick, Robert Resnick, Spatial Relativity. And all these discussions are very nicely presented there, why in transverse direction there will be only gamma and why in longitudinal direction there will be gamma cube. Means force, if force has certain angle with the velocity, acceleration, for acceleration you cannot just put the gamma mv in like that kind of thing. You have to be very careful. The direction of force and direction of motion means relative direction of force and motion. Then you will calculate correctly what is the acceleration in the direction of motion and transfers to direction of motion. Okay, so whenever in relativistic region, if you are calculating something, you should be careful.
Okay, sir. Sir, and then the 10th question. I think the answer should be 1, right? In the microtron, the revolution time of the first orbit may be equal to the
Yeah. Just we discussed it that in microtron we have two constants, A and B. First constant gives you that synchronization with respect to first orbit only. Means T revolution of the first orbit, revolution time of the first orbit is some integer multiple of the RF time period. Means A is that integer, let us suppose ATRF. And how will you synchronize the other orbits? So beauty of this thing is that the change in revolution time remains constant. The revolution time of the orbits will be different for second, third, fourth orbit will have different revolution time. So you cannot make synchronization for all the orbits simultaneously using same RF field. So how you will synchronize it? So there is successively change in delta t and that remains constant. So if delta t is synchronized with the RF time period, the whole microtron orbits will be synchronized at once. So just synchronize the first orbit and rest orbit synchronize using the delta t. Means delta t is the change in revolution time from first orbit to second orbit to third, and second to third, and then third to fourth. This is constant. So delta t is btrf. Let us say this b is some another integer multiple. So B and A, there are two integer multiples which defines synchronization in the microtron. Okay. So In any other machines, there is only one number which defines the synchronization. However, in microtron, there are two numbers which define the synchronization. The orbit with or synchronization with first orbit, and then rest of the delta t synchronization. Okay, this is known as dynamic synchronization because delta E is being synchronized rather than t itself. Now A and B, because of these two values, there are certain limitations. What are the values we can have? Now A minus B will be in the denominator. So A should be always greater than B. And the minimum value of B is possible 1. So A should be greater than 2 or equal to 2. Okay.
Yes, sir.
On the forum, I have completely provided this answer in written with details. So on forum, you can actually go and see the attached file in one of the persons, actually one of the students asked this question. So I have provided a very detailed answer there also.
Sure, sir.
Okay, so if we don't have any more question or anything to discuss, maybe we can end today's session. So, sir, can you, if you want, you can send me today's slides or the previous session slide also. I can upload it so that
Okay,
student.
surely.
I'll send you my email in the chat.
Okay. So I got it.
Okay.
PH20D092.
Yeah, it's
Okay.
my institute ID. Yeah.
Okay. I have copied it.
Okay.
I will send
Okay.
just now.
Okay. Thank you. Okay. And this recording I'll also upload so other people can also see everything. Okay, then. Okay, sir. Then we'll meet next week. And
Okay.
see you.
So,
Thank you. Bye.
Rohit, can you
Yeah.
repeat your email? PS20D
092
092
@smil.iitm.ac.in.
at the rate of what? What is that?
Smil.
Smail.
Yeah, smil.iitm.ac.in.
IIT. What is this Smail?
I think this is some domain of Gmail for
Okay.
institutes.
So it is smail.iitm.ac.in.
Yes, sir.
Okay. Thank you.
Thank you, sir. Okay, sir. See you then next week.
Okay.
Bye.
Bye. Thank you.
Thank you, sir.